First of all, I'd like to thank you. I would like to introduce myself. We are group number 5, Ahmed Abdelmohsen, volunteer. And you are going to speak about two different cases. Case number 5, electromigration until lit and tin free flip shape solder joint. And case number 6, tin whiskers reverse on lead free solders.
The other one, the black small black one.
First of all, before moving to our case study, we should be acquainted with the definition of soldering. Soldering is a process in which two or more items, which usually metals, are joined to each other with using a filling material or filling metals. This metal is usually with lower melting point than metal number 1 and the metal number 2. And we have here two different types. The first one here is lead-free, and second one is alloy of tin and lead. And we can see the two examples for using lead-free and tin lead in integrated circuit here, and for construction other material here. It is not a new trend in technology. It's used more than 5,000 years ago. There are two main types of lead-free solders that can be found in show. For instance, this number 1 is SAC 3.5, which contain different ratio of tin, sulfurs, and copper with melting point 270. Other types is SN 100, contains different ratio of tin, copper, and nickel and sulfurs, and melted at 228 degrees Celsius. And we can see this instrument here, which is used for soldering. It's used for connection shape to its baking substrate in a flip shape technology. Our case study is to understand the reliability behavior of lead-free solder. So now we can speak about our case study. Case study of electromigration. Electromigration is a problem in our solder joints, which causes eventual loss of connections or failure of circuit. Electromigration is due to transport of material. This transport of material is due to gradual movement of ions in a conductor. This is caused by the transfer of momentum between conducting electron and diffusion metal atoms, as we can see here in this example. How to get this? On the point?
Yeah. So you advance here.
Thank you. And here we can see here our metal cations here, and we can see our electrons. Transfer of momentum from electron to our cations cause migration of cations, which represent the metal atoms, which cause formation of void here at cathode due to migration of cation, and agglomeration of our cation here. In our case is palladium at anode. There are two main forces which affect on this migration. The first force is the direct electrostatic force here, which is a result of electric field which act in the same direction of electric field. The second one, which is due to exchange of momentum between electron and metals, cations, which you call the wind force. They used Black's equations to understand electromigrations. And to be sure, electromigration is the reason for the failure of electric circuit. The experiment was operated on 10 lead solder joint of 125 micrometer in diameters. It's used under this condition, 3 multiplied by 10 to the power 3 ampere by centimeter cubic at 150 degrees Celsius for a few hundred hours. This is the experimental setup of our work. Experimental setup to study the electromigration on flip shape eutectic 10 lead solder joints. As we can see here, we used electrodes for the applied current from covered lines on substrate. The experiment was operated at temperature from 100 to 140 degrees Celsius. Average applied current density, as we can see here, in this range. And the contact window is diameter is 100 micrometer. Electromigration failure was monitored by studying resistance change by times, by studying 24 samples. We studied the change in resistance, and we can see here the resistance is constant, nearly constant, starting from 0 to nearly 45 hours. And there is a significant change in resistance at 45 hours is due to the failure or the loss of connections due to decrease in contact area caused by electromigration. We can have more information and see the process deeply by using a scanning electron microscope. First of all, it's here before applying any current or before electromigration. Here, as soon as we started electromigration, it's after 38 hours to initiate the first few voids, and only after 5 hours to have complete failure. What can we understand from these two conclusion or information is the failure of our circuit is depending on the nucleation of void more than the void formation itself. As soon as it started, as soon as failure took place. And here we can see the atomic flux diversions which occur at the upper left here, the position of entering of current. Current enters the pump from this direction. Vacancy accumulation takes place followed by void nucleations. This followed by condensing vacancy. So we can see here at certain times void spreads through the contact and failure take place. At the same times, we can't forget the accumulation of metal cations on the anode material due to migration of cation, because it's simultaneous process take place at the same times. Another experiment set up using a thin film strip electromigration was studied at current density 10 to the power 5 ampere per centimeter cubic. This experiment took place at room temperatures for 5 days. And we can conclude from this experiment, we have the same K observation, the formation of void here at cathode, formation of helix or agglomeration, but it's here it's different due to the formation of tin and lead. It's operated at 100 degrees Celsius and 140 in this range. Before 100 degrees Celsius, tin is faster than lead, so tin is the stem of this agglomeration intermetallic compound. At higher temperatures, lead started to form the capping of this tin. So it's very difficult to do study here acceleration test at certain temperature. So we should do systematic and accurate study at a range of temperatures in order to get the right information and the right mechanism of failure of our circuit. We should work in a range of temperature to know the right mechanism of failure. As the diffusion species different at different temperature, as I mentioned in details here. Polarity also should be considered here as due to the same reasons. The same reason is the migration of cations from cathode to anode, or called the dissolution and agglomeration of these metals at anode. Also, we can speak about the solution of nickel phosphorus UBM. It's well known that as soon as nickel in the solder joint which contain nickel, as soon as this nickel started to migrate to anode and agglomerate, it should be compensated from the nickel presence in the UBM. So nickel started to dissolve it and migrate to compensate it in the solder joint. So we can see here before starting of electromigration, here we have UBM to complete represented here. It's decreased here due to migration, and here is this appeared. And the failure in this case is due to two main reasons. The first one, losing of UBM. Second one is dramatic change in composition of solder joint due to large amount of intermetallic compound formation. Analysis. Design rule of our work here is to work on 1 ampere over 5 solder pump or 0.2 ampere over 1 pump. So electromigration again and again is due to the main two reasons in solder pump, thin lead, low melting point, and high atomic diffusivity of atoms. At room temperature, of course, cellular precipitation takes place and the tin whisker grow on tin surface followed by formation of lead in the surface. Self-diffusivity in tin lead layer interface about 10 to power 8 centimeter cubic by second. Diffusion distance is 1 micrometer is expected in 1 second. Second reason for electromigration here is the large current density change. You can see here we have a geometry, different geometry. We have here this geometry with a specific diameter, but here at the contact point, the diameter is depleted. So for instance, if we are working at the 50 micrometer diameter, the current density will be 3 multiplied by 10 to power 3 ampere by centimeter cubic at this condition. Here it will be increased to 10 to power 4 ampere to centimeter cubic due to, as I mentioned, the stringent geometry and hence interconnection line and solder pump. So large current crowding at interface is the second reason and should be considered. In case of say UBM, current crowding occur in UBM rather than the solder. Yes, for instance, if we have two different joint solder, the first one with 2 micrometers of UBM here, so current crowding regime is outside UBM. But we have here this 10 micrometer UBM, so current crowding regime is inside UBM. Measuring atomic flux of electromigration. How to measure the atomic flux of electromigration? To use something which called inert particles. These inert particles here, as we can see, these inert particles are put in these positions before starting electromigration. As soon as we started our experiment to measure electromigration, these inert particles, which we call the markers, started to move. But we can see here something which should be considered. It is not at the same condition. It started from this point and stop at this point. This is for two main reasons. The first reason is current crowding, which is different from side to side. Second, the most important, is differential displacement in tin and lead rich region. There is a region rich by tin and region rich by lead, regardless of its electric homogeneous. This effect on this inert particles. We can get information about displacement, time, cross-section area. In this case, we can use these equations to be acquainted and have information with electromigration flux and charge numbers. And here we have these two curves about the displacement markers here for different types of markers. This type of marker at 0 hours, 20, 30, 39.4. And here displacement markers against time at different times, markers change its position. And hence we can have information and start our calculation. Summary. Electromigration is a problem in microelectronic device. We can't get off electromigration 100%. It's very difficult, but we can decrease electromigration. For instance, if we use 10 silver covers, and we can measure electromigration in this alloy against to silver against to tin lead alloy. Electromigration here is lower than the first case, hence we can find an alternative one. And this issue needs more intensive study, of course, which is, there are many papers already reported all times. And for materials there is a reference, and you should care to find and to match each image to each. And I will handle it now to my friend.
Okay, so I will talk about the whiskers, the thin whiskers grow on lead-free solder. And well, what happens is that when we have, for instance, here we have a lead frame for mount surface technology, and when we replace the lead for another substrate like thin copper, we formation of whiskers. That is this, like this, we can see here. And it has been observed that the growth direction and the length of the whiskers is around the lattice constant size of the thing. So the growth rate is about 0.3 millimeters per year, and the problem is that this is fast enough to cause a short circuit in few months. So as we can observe here, a short circuit can be created between the neighboring lengths of the lead frame. So we are facing here a reliability problem, and the main goal would be to find a test for the whiskers and find a way to prevent the growing of whiskers. And for this, it's very important to understand why does this happen. So we'll start presenting some experimental observations, and we can see here as SEM pictures of a thin copper finish surface and on only thin surface, finish surface. So we see that the morphology of the whiskers is very different, and here they are kind of fluted, but here they are more facet, and here they bend on sharp angles, and we can see that the diameter of the whiskers is about some micrometers, which is very similar to the grain size of the matrix. But the most important remark is that the rate growth of thin copper is faster than the gray growth of thin. And here we have a TM picture, and we observe some defects that could be dislocation on the whisker. So let's address these questions. What is the reason for whiskers growth? And why does it happen at room temperature? What could be the driving force that leads to this formation of these defects? And why does it grow on thin and not on copper? So from the pictures, we see that we are facing a relief surface problem, and so the origin could be the relief of compressive stress, and we also observe that it grows from the bottom. So the source of this compressive stress can be mechanical, thermal, or chemical. But let's focus on the chemical source. Why? Because we know that there is a formation of intermetallic compound at room temperature. So some experiments were performed on very thick quartz, which means that there are not mechanical stress, and some whiskers, we observed the formation of whiskers. This means that the reason is due to the formation of the intermetallic compounds. And what they analyze is that the thing starts diffusing along the grain boundaries of itself, and this stress needs to be released by atomic rearrangement. So the atoms diffuse to the root, and they push out the whisker. But then we solved the question, why does it happen at room temperature? And it's because of the intermetallic compound formation. What could be the origin? But we need to answer why does it grow on zinc and not on copper? And the answer is the formation of a surface oxide. And it's because only metals like zinc can grow protective oxides, and this blocks vacancy sources and zinc that this could release the stress. So as we can see in this picture, when the oxide is broken, there is a formation of a whisker. However, it shouldn't be so thick because then it cannot be broken. And some important remark, we also observe that this growth is localized, and this can be explained by the fact that there could be a discontinuity in the crystallographic orientation on this spot, but still this is just a hypothesis and it's not something proved. And here, they present some results, and these results support the idea that the main driving force of the whiskers growing is the formation of this compound. And X-ray diffraction shows some peaks. Okay, this was performed on a finish of copper and zinc. And here they wanted to look at the cross-section of a whisker. So they did focus ion beam, and they etched two holes here. And what they observed was that many grain boundaries precipitates of this intermetallic compound. So this make us conclude that is due to, well, this supports the idea and explains why when we have only thin, the growth formation is slower than when we have zinc and copper. So as a conclusion, as Ahmed explained before, electromigration could be a good way to perform an analysis, and can be done at room temperature. And to prevent the whiskers growth, it has been found that a thin layer of nickel can work like a diffusion barrier between zinc and copper, since the reaction between nickel and zinc is slower.
Thank you.
Any question?
At the beginning of your presentation, you said it's animation technology. And the first few slides, I remember. I'm just curious to ask you about that.
What do you mean?
Yeah, you said it's ancient technology. I didn't understand.
You say that soldering is very ancient.
Yes, it's very ancient. Yes, it's very ancient. It is not a new trend.
Since the age of
yes, 5,000
bronze.
years ago.
Yeah.
For instance, here it's used for jewelry items, cooking, ware, and the tools. Since
people
5,000
have
years ago.
used this the method of resolving by humans since a long time ago. Bronze Age.
Yes.
Very long history of soldiering. They did not call soldiering at this time. No? No question? Is electro-migration a problem nowadays for joining and not for other things inside the IC and so on? This, for example, one of the dimensions are some hundred of micrometers. Is a problem? Can it be a problem, or in the future, or nowadays, or in the past, or if we compare electromigration, not let's say inside the chip, only for joining.
For joining now, it is not a problem 100%. Because, as I mentioned, it's a problem, but it can't be eliminated, but it can be decreased to reach the optimum working condition for our.
Yes, but in the
solution.
future, let's say, in the future or nowadays, because before the diameter of soldiers and so on was 1 millimeter. After that, some hundreds of micrometer.
Yes.
So the intensity of current was not so very high. But nowadays, you use copper pillars with a diameter of, let's say, 20, 30 micrometers, 50 micrometers. And in this case, it can be critical, of course, because the diameter is very high compared to the, let's say, to the plots of copper and aluminium inside the chip. But nowadays, the currents are sufficient high that this can be a problem. Pay attention with colors. Yeah. So don't use this kind of colors.
Personally, I'm colorblind. I cannot see anything on your slide. Not at all.
Because
it's quite common.
void formation of cathode and so it's very difficult to read that. So because you have a combination of
And your conclusion never
and
puts
sometimes
red on black.
you had some even at the bottom some text which cannot be read.
Yes. Okay.
Yeah, so pay attention to that. And another thing I would like references. Try not to use, let's say, from websites. You can use some of them, but it's better to have journals and books and so on. Not all the references. You can use one or two. It's nice because publicity, marketing, and so on.
Yes.
Websites. But you need also, and above all, to give references, other references from books or so on. And it was okay. It's just you have not analyzed the, let's say, the kinetic model that was presented here. It's nice just to have an idea how the chemical forces and so on gives this very strange phenomenon, whisker, which is even nowadays not very well known how to prevent it. So. Okay, so thank you, for all presentations. Good work, and see you in the day for exam.